So now we're going to take a look at Poisson critical regions. As a Poisson distribution is also a discrete distribution, we find the critical regions in the same way as we did with the binomial distribution. So we're going to have a look at some examples. Again, like I said, it works very similar. And again, if we go to Poisson, we have an inver per that we're going to be using to help us to find our first value that's going to give us a rough estimate of where we need to start. So the number of breakdowns per day of a lift in a block of flats can be modelled using a Poisson distribution with a mean of 0.2. The maintenance contract for a lift is awarded to a new company. They decide to record the number of breakdowns every 30 days and perform a hypothesis test on a 5% significance level to determine if the average number of breakdowns has decreased. Find the critical region for this test. So, because we have 30 days instead of a day, we're going to start off with x follows a Poisson distribution with a mean of 0.2. And this is for 1 day, and then we need to change this to 30 days, just as we did with the Poisson distribution. So we need to have 0.2 times 30, which hopefully gives us 6, and it does. So then back into my stats function. Like I said, we're going to use the Poisson inver per to help us to get a good starting point. Again, this only does areas to the left. Here we're seeing if it's decreased, so we're wanting 5% to be on this left hand side. So that means that we're going to have area 0.05 and our lambda is 6 because we're looking at 30 days. And that gave us 2. So we're going to start off by having a look at the probability that x is less than or equal to 2. So then going to dist across Poisson, PCD. Our lower is 0, our upper is 2, and our lambda is 6. Remember, if you have one of the old types of calculator, you're just going to have x and mu. Your x will be 2, your mu will be 6, because remember the mean is the same as the variance, which is the same as the parameter, which is lambda. So that gives us 0.06196888, which is more than 5%, so that's not our critical value. So let's try less than or equal to 1. Which gave us 0.01735126. So 1 is our critical value, it's the first value inside our critical region, and 2 is the first value at which we would accept H0, which means that our critical region is going to be when x is less than or equal to 1. We'll have a look at a two-tailed example. So here we have, at a mill, 3,000 metres of cloth are produced per hour, during 1 hour, Using a 1% significance level test, the miller owner claim is investigated on an hour's production to test if the mean number of faults in 0.02 metres. Find the critical region of this test. So we've got 0.02 per metre. We're doing this for an hour's production. We know that in 1 hour, 3,000 metres are produced. So we need to change this from 1 metre to 3,000 metres. So again, back into our normal calculator. 0.02 times 3,000. And this time we get 60. Because it just says that we're seeing if it is, not if it's more than 0.02 per metre or less than 0.02 per metre, that means that we have a two-tailed test. So we're wanting half of our 1% at this bottom end and half of the 1% at our top end. So back into the distribution across the Poisson inverse. This only does areas to the left, so we'll start off by having a look at this bottom one here, so 0.005. And this time our lambda is 60. And that gave us 41. So then we're looking at the probability that x is less than or equal to 41. And that gives us 0.0060822. So that's too big. So we'll look at the probability that x is less than or equal to 40. Which gives us 0.0039828. So 40 is our critical value at this bottom end, and 41 is the first value at which we would accept H0 at this bottom end. Now we're going to try for the top end. So this time, because this only does areas going to the left, we're going to have 0.995. Because if we have 0.005 there, this whole other bit here is going to be 0.995, which gives us 81. So then we're doing the probability that x is greater than or equal to 81. If you have an old version of the calculator, remember you're going to have to change that to the 1 minus the probability of x being less than or equal to 80, because this is discrete. So this time our lower is going to be 81. Our upper is going to be a really big positive number because we don't have an upper limit to the Poisson distribution. And that gives us 0.0056317, which is too big. So we're going to have a look at the probability that x is greater than or equal to 82. Which then gives us 0.0040122. So that means that 81 is going to be the last value at which we're accepting H0, and then 82 is going to be our critical value at the beginning of our critical region at this top end. So that means that this time our critical region is going to be when x is less than or equal to 40 and when x is greater than or equal to 82. So I'd now like you to pause the video and give the two Now You Try questions a go. So hopefully you paused the video and you gave the Now You Try questions a go. So for this first one, we've got the number of telephone calls received by a company follows a Poisson distribution. Over a long experience, it is thought that the mean is 8 calls per hour. This is tested at a 5% significance level to determine if the provider's significant evidence of a change in the mean number of phone calls per hour. Find the critical region for this test. So we have 8 calls per hour, and then it just says that we're testing it per hour. So we're not changing our what we're looking at this time. When we go into it, we've got a two-tailed test because it says change at 5% significance level. So we have to halve that 5%. So we have 0.025 at this bottom end, 0.025 at the top end here. Using our inverse P, that gave us 3. Looking at the probability of x being less than or equal to 3 gave us 0.04238011, which isn't smaller than 0.025. So we tried a smaller number, which is the probability of x being less than or equal to 2, which gave us 0.0137536, which is less than 0.025. So that meant that 2 was our critical value at this bottom end, and 3 was the first value at which we would accept H0. Then at the top end, this time in inverse P, put in 0.975, gives us 14. Then looking at the probability of x being greater than or equal to 14 gives us 0.0341807, which is too big. It's not smaller than 0.025. So then we had to try probability of x being greater than or equal to 15, which gave us 0.0172569, which is our critical value. So that was the first value in our critical region here. So our total critical regions is going to be when x is less than or equal to 2, or when x is greater than or equal to 15. And then for the second Now You Try question, We had, in a particular town, rainstorms occur at an average rate of 2 per week and can be modelled using a Poisson distribution. Over a period of 8 weeks, so we had to change it from 1 week to 8 weeks. So you can see there I've times by 8, so my parameter of 2 is now a parameter of 16. Is recorded and tested to see if the average number of rainstorms per week has increased in the town. So this is a one-tailed test and we're looking for an increase. Find the critical region of this test. This time it doesn't tell us the significance level. Remember, if you're not told the significance level, that means that you are using 5%. An increase, so we're looking at this side with our 0.05. When we use inverse P, our area is 0.95 because it only does the area to the left, which gave us 23. Looking at the probability of x being greater than or equal to 23 gave us 0.05824092, which is too big. It's not smaller than 0.05. So then we tried 24, x being greater than or equal to 24, which gave us 0.03668565. You can still see that in my calculator. It's got a bit smushed together here at the end. Which is small enough. So 23 would be the last value inside our accept H0 region. 24 is going to be our critical value, which means that anything bigger than that is in our critical region. So the critical region is going to be when x is greater than or equal to 24. Please remember, if you do not have the inverse, the inverse binomial, or the inverse, the inverse Poisson, function in your calculator, you are just going to have to try numbers until you end up with that change between being inside the critical region and not inside the critical region, and that shows you that if those two numbers are consecutive, that you have found your critical value. So please be careful with that, and you have to show this working like I have on all these questions, showing the last value that's in the accept H0 region and then the first value that's in the critical region, because that is going to be the critical value when you stop accepting and start rejecting your H0. Thank you very much for listening.